Hi, everyone. My name is Ranger Liu. I am a second-year PhD student at the University of Washington in Seattle. And yeah, today I'm going to talk about transit information density as an artificiality metric for transit-based technosignatures. So first of all, why are we interested in transits for technosignatures? As you can see by this graph, and as we all know, over the past 30-odd years, that the transit method has become our most successful technique for planet detection by far. So we think it's sort of likely that extraterrestrial civilizations might decide to create artificial transits to broadcast their existence because transits are so useful and relatively easy to detect for any kind of astronomically inclined civilization. So when we're looking for transit technosignatures, what we're really looking for is anomalous transits, like the talk before had previously talked about. A lot of the previous investigations of anomalous transits, like, for example, this one from Wright et al. 2016, and also this one from Arnold 2005, these are proposing various unusual geometries of single transits, but these have yet to be found in any extant data. But if you consider instead anomalies of multiple transits, we do have this odd case of the random transitor HD 139139, which is found in K2 data. And Rappaport et al. 2019 had reported this as having these 28 transit-like events that followed no apparent periodicity. So here the anomaly is coming from the pattern of multiple transits rather than the geometry of a single transit. So this is what we're interested in, is the potential for artificial patterns of transits where maybe any single transit looks kind of normal, but the overall pattern is quite strange. And we want to think about this as like maybe one way that these artificial patterns could be made is by having a single artificial orbit, occulter pudding orbit, which has the ability to change its radius, maybe through some kind of variable aperture, maybe something like a JWST sunshade-like megastructure. And so then by changing its radius, it can change the depths of its transits. And these transits would occur at regular intervals as this thing is orbiting around its star. And so you'd be able to encode some kind of a message using these varying depths. So with this potential scenario to create artificial transit patterns in mind, we want to think about the question of what kinds of multi-transit patterns would make good SETI beacons. So we can first try and take a step back and think about what makes a good SETI beacon in general. And we're going to think about this in a similar manner as Sheikh's 2020 9 axes of merit, which I'm sure we're all very familiar with. For our purposes, we want to think more from the perspective of a broadcaster, right, who's trying to construct some kind of signal. So we came up with this analogy of being a musical busker on a noisy street. So we can help define some criteria that we might consider when we're trying to design this kind of beacon. So we first think about loudness. As a busker, right, you need to play loud enough to be heard over the background noise. And so your signal needs to be distinctly artificial against the natural background. So this is similar to the Sheikh's axes of detectability and ambiguity. Our second criteria is melodiousness, right? You need to play with a melody. Your signal should demonstrate intentionality or knowledge in some way by being structured and perhaps in some mathematical way. And this is kind of like in, Carl Sagan's Contact, when the beacon that they intercept is made of prime numbers, which are very clearly intentional because of their mathematical structure. Next, we have catchiness. So your music, right, should be very quickly recognizable to catch somebody's attention. And similarly, the signal should be able to be received within a short period of time. This is more of a logistical constraint that a good beacon should not require extremely long periods of observation. And lastly, we have persistence. You have to keep playing your music for a long time if you want to maximize the chance of people hearing you. Similarly, a good beacon should be broadcast pretty much continuously because so that it doesn't prefer any particular window of observation. And this is pretty similar to Sheikh's axis of the duration of a technosignature. So these are our four criteria. And so you can think of maybe like the ideal beacon as being equivalent to somebody who is playing a very loud and very well-known tune on the street, maybe from, dawn until dusk, which would probably be pretty annoying to hear, but that's the the goal here. And so we're proposing these not necessarily as orthogonal axes, but just to offer a kind of conceptual framework for judging potential beacons. And you can sort of notice that these first two are kind of more about structure or content, and then the second two are a bit more about temporal logistics of observability. And as a shorthand throughout the talk, we're going to put these four criteria into a kind of scoring card that we can use to grade our potential beacons, ideally by quantifying each of these parameters. So finally, we want to specify these criteria to our particular case, so thinking about beacons made of transit patterns. So loudness we will define as being distinguishable from being both periodic and random transit patterns. Melodiousness will be an artificial transit pattern that follows some mathematical or otherwise structured pattern. Catchiness will mean that the signal is recognizable within a small number of observed transits. And then for persistence, we want to have no long stretches without transits. So as we'll see a little bit later, that catchiness and persistence are actually pretty easy to quantify, and melodiousness is pretty easy to ensure. But loudness or artificiality is a bit harder to quantify. So our approach is to first define a quantitative metric for the loudness or artificiality of transit patterns. So that is transit information density. So to build this metric, we're going to borrow from information theories, borrowing the definition of information content or surprisal, in which a message that is composed of likely events has a low information content because it's not surprising, and one that is composed of unlikely events is high content because it is very surprising. So we extrapolate this into the realm of transits to define transit information density, or TID, such that the more natural a transit pattern is, the lower its TID, and the more unnatural its pattern, the higher its TID. And we will quantify this naturalness simply as NP over NT, where NP is the number of planets needed to reproduce the transit patterns based purely on periodicity, and then NT is the number of transits in the pattern. And we can sort of see that this definition fits our expected behavior, right? So for a natural system, then P will always stay constant and relatively low. And then as we observe more transits as NT increases, TID will thus decrease, and so it should sort of asymptote directly to zero. So now that we have this definition, we're going to look specifically at binary signals to start, just the simplest. So again, if we're thinking about a kind of artificial Fourier aperture, this would just be two states, one that is like sort of closed all the way up, so you see nothing, and then one that is open all the way to create a transit. And so we want to define behaviors of periodic and random transit patterns so that we know what we want to avoid in our beacons. So this plot here is showing the TID behavior of periodic and random signals in the simplest binary case. So the periodic signal is just one single planet, and then the random signals are randomly generated element by element, choosing either from 0 or 1. And so here on the y-axis, we have that TID, NP over NT, and then we have increasing number of transits on the x-axis. So you can see that asymptotic behavior here from that periodic signal as we expect, which follows exactly a 1 over x trend. And then our random signals are of 1,000 trials of random signals also have this clearly defined behavior that kind of carve out this middle part. And we've marked this out somewhat generously using a couple of piecewise functions. And so then we see that there are two potential areas for our very loud or our very artificial signals to live. One is this high TID regime, which is entirely above the random regime. And then we also have the mid TID regime, which is between random and periodic. So now that we defined a way to quantify loudness, we want to move on and try and find specific signals that might be good SETI beacons under our criteria. So we're first trying to build signals that fill 3 out of the 4 criteria: loudness, catchiness, and persistence, and then sort of analyze the results in terms of melodiousness. So in trying to find loud signals, we're going to focus still in the binary case, and then we're going to target this high TID regime because it's sort of farther from naturalness than the mid TID regime. So it's kind of louder in that sense. So we use a really simple algorithm to build a signal one element at a time, and we tell this our algorithm to maximize our TID so that we can ensure our loudness or artificiality. And then we also tell it to obey this kind of silence limit L, which tells it to have no more than L null transits in a row. And that is to ensure persistence or continuity, which we defined previously as having no long stretches without transits. So this is an example of a signal that has silence limit of 5. So there's no more than 5 zeros in a row. We then built 40 of these loud and persistent signals. We tested silence limits from 1 to 20 for signals starting either with a 0 up here or starting with a 1 down here. So these are all the behaviors of those signals. And then for each of these signals, we quantified the kind of catchiness by calculating the number of transit it takes to reach distinction from randomness. We calculate that in 2 slightly different ways. And finally, we chose our best high TID beacon as this one, which had the lowest silence limit and also the lowest DFR, so the best catchiness score as well. So we can fill out the scorecard for this signal, which is very loud and has a catchiness score of 23 and that persistence score of 6, the silence limit. But if you look at the first several elements of this sequence, it's not really melodic at all. And we can sort of test that by inputting it into this online encyclopedia of integer sequences, at least to compare against any mathematical structure. And we see that it follows no real mathematical structure. So musically speaking, we can maybe say that this is equivalent to somebody who is constantly blaring, a very loud air horn, but with sort of erratic durations. So it's very loud and persistent and kind of catchy in that it's instantly attention grabbing, but it's not particularly melodic. So next we tried to look for signals that are melodic, catchy, and persistent. And so since we defined melody as having some kind of very clear structure, we chose to test this sequence through Morse, which is a simple and aperiodic but very structured integer sequence. You can kind of think of it as a more fractal binary version of Fibonacci. So because it's a mathematical sequence, it's very definitely melodic. Because of the nature of its construction, it is quite persistent. It has a silence limit of 2. The catchiness and the efficiency is sort of harder to quantify because this really becomes a mathematical question of like how long a subsequence needs before you can identify a mathematical sequence. So we kind of leave that as an open question. And then we also ask whether this signal is loud or artificial by plotting its TID behavior. So unfortunately, as we see, it does fall very squarely within the random regime, so it fails our loudness criterion. So here's the scorecard where we can see that it is melodic and pretty persistent, and we'll give it maybe a tentative maybe for catchiness. So musically, we can maybe consider this as being equivalent to somebody who is very quietly playing a tune, but maybe a tune that is not as well known, maybe a more niche tune. So here are the 2 binary signals that we tried so far. Here's our high TID and our through Morse. So we have the sort of loud, erratic air horn versus a very quiet and more niche tune. So thus far we've focused on the binary signals. I'm going to show a quick application of TID to multivalent signals. So again, these would be signals in our sort of hypothetical scenario that would be created by opening our variable aperture to varying sizes to create varying depths. So we can play a similar game and define the boundary behaviors here of periodic and random signals. And here I'm showing the behavior for binary, trinary, and quadral, so 2, 3, and 4 possible states. You can notice that as you increase the valency, right, that the random regime also moves slightly upwards, and that kind of maybe aligns with our intuition that having more nuance in sort of more possible states might translate into more information content. And then the periodic 2 and 3 planet signals here are following 2 over x and 3 over x trends, as we would expect. So to apply the multivalent TID, we did a very simple test analysis on the TRAPPIST-1 system, of course, which is extremely multivalent. It's got 7 planets. So we used orbital parameters that were given in the 2017 Nature paper on TRAPPIST to turn some transit data here into a quantized signal of each of those transits. And then we calculate its TID behavior in this graph here. So you can see that it's very obviously periodic. It's got that kind of asymptotic slope down to 0 as we want. And then these bumps are just sort of showing that as the signal kind of includes more and more planets, that the TID is kind of recognizing those planets and adjusting accordingly. So this is a pretty simple application, but it's a good kind of first order verification that TID is able to detect periodic signals in multivalent cases. Yeah, so it's periodic. So lastly, we also attempted a similar analysis of the random transitor, which we remember was our initial inspiration system for looking at anomalous transit patterns in the first place. So we did a very simple 4-state split on the transits reported in Rappaport et al. 2019. And then when we analyzed this quantized version of the light curve, we do find that the random transitor signal falls squarely into the random regime for quadral signals. So this seems to agree with Rappaport et al. 2019 that the pattern of the transits is essentially stochastic and sort of random. So by our standards, that would mean that the random transitor is not a great beacon necessarily because it fails our loudness or artificiality requirement. So in the multivalent cases that I'm presenting, I am sort of glossing over a lot of complications that arise when you try and do this multivalent calculation. But again, I just want to show it as a way of sort of confirming that TID does work in multivalent cases. It needs a little bit more tweaking maybe to get a really robust calculation, but it definitely works. And we get this kind of bonus corroboration of the randomness of the random transitor. So in the last few minutes I have here, I'm just going to return to our 2 binary signals that we talked about before and kind of think more through what these signals really mean. So it seems like the catchiness or the efficiency or the persistence and continuity are pretty easy to engineer or select for, which is kind of encouraging because we generally would want to create a signal that is very logistically observable, right, in a temporal sense of saying that you don't need a really long observation window and you don't need a very specific observation window. But in terms of the content, right, it's much harder to satisfy both loudness and melodiousness at the same time. So there's a kind of open question of which one is better. Because we've quantified loudness using this TID metric. Maybe you can imagine that it's might be easy conceptually to sort of pipeline this process to automate a search through a bunch of existing data. And then melodiousness seems to be harder to quantify. And so maybe it's harder to automate a search for kind of melodic signals. But maybe it's also more convincing because it displays some sense of knowledge, right, and intelligence somehow beyond just gaming a metric. And so I'm still sort of interested in trying to find a signal that fulfills all 4 of our criteria. And so I'll leave you with an example that shows how crazy you can really get with trying to build and test melodic signals. So this is work that I did with an undergrad researcher, Ishani Parang, who has a poster on this in the poster session here. So you should definitely catch the poster in a few days.
2 minutes left.
Okay. So basically, we take the tongue twister, she sells seashells, you break it into 4 sound chunks, encode it into binary, and then we use these sound chunks and this phrase's consonant vowel pattern to create combinatoric variations of the phrase. So the signal is basically combinatoric scheme derived from linguistic patterns. So it's got a lot of mathematical structure, it's very melodic, it's also very persistent, sounds limit 3. We have the same open question about catchiness, and then we did calculate its TID to check for loudness. So you can see that it's still in the random regime here, mostly, but towards the tail end, it kind of seems to creep out a little bit. So maybe there is some hope to finding a signal that is both loud and melodic, but maybe we just need to get really super creative with our encodings. Okay, so that is the end of my presentation. Thank you.
Thank you very much for your talk. So we have one question, and we can start for you, and then we switch probably to Claudia, and then see maybe more questions for you also come up. So the question is, Caleb Strom is asking, do you think this varying signal would be direct communication, or would it be more likely just be a regular pattern that is a sign of intention, but not necessarily communication? For example, a telescope making regular observations.
Yeah, I think like, sorry, I'm just trying to find the question. I think that we're trying to think of the signal as being like intentional communication. So trying to think from the perspective of constructing a beacon that is like meant to be as conspicuous as possible. But of course you can think of, I guess, like lower tiers of intentionality of like maybe if this object or whatever the thing is that's causing this pattern is not necessarily trying to communicate something, then maybe it will be slightly less intentional somehow. Yeah.
All right. Thank you so much. We will wait for more questions for you. And I suggest that Claudia, you unmute yourself and also join the discussion. We have a few questions left for you. So
yes,
from Vishal Gajar, suggesting that looking at gradient of flux as a function of planet phase would be more interesting than just delta max. What do you think about that?
Yes. I mean, what I've mainly looked at is how we typically look at base curves for planets, which is the flux ratio. So that is the flux ratio planet to the star as a function of planet phase, or where the planet is in its orbit. So I guess that is easier to compare to what I've found in previous observations and models. And I mean, we are looking at a ratio, not an absolute scale. I'm not sure if I understand the question fully. But I mean, taking the gradient or the derivative with respect to time, since the phase curve is changing rather drastically, I mean, that could be a way of filtering out potential candidates, since we are looking at something, or we are looking for something that changes quickly. But it's not something that I have considered, but it could.
Yeah, he argues that because the scale might be not so easy to determine. Also, in the previous question, that star could be variable, so maybe this gradient with sharp increase would be a signature. All right. So Benjamin Fields also asking if solar sails, light sails, can be detected in similar way if they are not at Lagrange point.
Yeah, I'm not an expert when it comes to solar sails, but I would imagine these being smaller structures, and I guess it depends if they are like above the flux ratio also that the telescope can detect, because even though like previously we've been able to detect planets with flux ratios to the power of, say, 10 to the power of -5. And now we're looking at planets with flux ratios 10 to the power of -10, maybe a bit lower, around that number, but we're still like, it's still in the limit of like Earth-sized planets. So we would probably need large structures, even if they were solar sails. So I guess it depends, and they still need to be, of course, inside where the HWO look for planets. So it would still need to be something highly reflective and a large scale structure, I would say. So not if it is just a small solar sail, and especially if it's not close to the planet. Yeah.
All right. Yes, and Joseph Lazzo also argues that it could be the distance to the solar sail plays a role, of course. Yes, how far it is from the star. All right. Then, yes, coming back to the cost, maybe I misunderstood the question previous time. That Eric Corpula says that building star shades for telescopes around alien planets wouldn't be cost effective in this way. the big ones. He suggests maybe swarm of such star shades would be there, and then it's maybe because it will be more cost effective, and maybe it's good to check that signal as well.
Yes, I briefly mentioned in my article like alternative star shade geometries, because this is not necessarily the best one. I think it is something that would give a large signature, and maybe if it was a swarm of something in orbit around the planet, it maybe would be more similar to clouds or more difficult to detect. I am not sure, but it's actually, or it could be something that is like more within reach if we compare to our own technology to put like star shades in orbit instead of the planet. But yeah, it's definitely something that should also be looked at, in my opinion.
Okay, thank you. I encourage audience also to ask questions to Sarah. She's also here, so if we have time to discuss all three talks, and please feel free to ask questions also. Right, so let's continue with Claudia still. So the question from Juan Carlos Beamin, whether we can confuse star shapes and Dyson spheres with your, or kind of detect Dyson spheres with a similar
yeah, I saw some people wrote a bit about this under the questions as well, but I think the main difference is that the Dyson spheres would be close to the star instead. And here we do look at the planet, and the total signal of a star shade plus a planet, and the Dyson sphere would be where the star is instead. So I don't think they are easily confused with each other, since we are looking at different things at different distances to the star. And also in this case, if we're looking at HWO, we are blocking out the light of the star as well. So it's not really something we would see in the observations.
Yes, I mean, you mentioned around the star, but one can imagine the Dyson swarms also, which can be around stars or planet. They were suggested previously also in other papers that could be around planet as well. So that may be worth to check as well.
Yes.
Okay, let's move on. So we are done with Dyson swarms. Are there questions to Ranger and Sarah as well? If not, I maybe go back to Sarah's talk, and I will ask also a signature of clouds, because at this near infrared range and mid infrared range, we would see also signatures of clouds. And you said that they are not solvable. These fluorides, they're not solvable in the water, but can we expect any condensates from them, and which form the clouds?
Well, I don't know about NF3 and FF6. I haven't heard of the molecules I talked about being like cloud condensation nuclei, but possibly.
Yeah, that would be interesting to check. If some exotic conditions are there, then maybe they can condensate. All right.
Well, I was going to say, I mean, yeah, I think we may have run out of Q&A for now. But I do think there's a whole host of other ideas that haven't been put out there yet, like microplastics. If people read about microplastics, they're everywhere right now. I mean, hopefully it's just short-lived for our technology that we're going to get a handle on this, but they're impossible to get rid of in wastewater. You know, I have this like miniature plastic kettle. It's like for a camper. And I'm like, wow, should I be really drinking out of heating up my water like on this plastic? It is. It's like rubber. But microplastics are everywhere, and some of them are small enough to float around in our atmosphere. So I'm sure that there is a cloud-like type of technosignature out there. I just haven't seen it written about yet.
Right, thank you. I have a question to Ranger as well about regular patterns. In principle, there are stars, many stars show regular patterns due to stellar periodicity. On star spots or pulsations, the signals could be smaller or larger. Do you think we can distinguish these artificial signals from the stellar signals in this way?
Yeah, I think the way that we construct the metric, at least, is like is sort of measuring the kind of distance from periodic for any signal. So any periodic signal, whether it's related to the transit in particular, or I suppose to the star spot activity that is sort of globally periodic, would fall in the non-artificial range.
Okay, thank you. All right, there is one more question for Sarah. How likely would it be detect the molecules you discussed as a geo engineering project, terraforming project?
Right. First, I just want to go back to microplastics, where someone says there's evidence that microbes are evolving to digest them. As you notice, I said I hope it's short-lived here, whether it was microbes or us finding a way to get rid of them, which people are working on. Okay, back to SF6 and F3. Our Earth, we're producing sulfur hexafluoride and nitrogen trifluoride. They're used in industry, so they're just leaking out. Like, they're not intentionally there. So it's always going to be tiny amounts, like parts per trillion. That's why I emphasize brand new paradigms to detect, like solar gravitational lens telescopes, something like LUVOIR or Darwin or Life would never reach. We saw from Eddie Schwieterman's quoted, the few things I quoted from his abstract, that a civilization that really wants to greenhouse warm for whatever reason, it's like 100 part per million, which is way more than parts per trillion. So it would be way, way easier to detect that. And that's probably within reach for Life, the new Darwin-like mission out of Switzerland.
Yes, that would be fantastic. Called Life. Yes. All right. Do we have more questions? Yes. To Ranger. All right. Do you see the question? I am reading as I see it. So.
Yeah, I see the question.
So I don't know if it's recorded when we are in video. I'm not sure. Should I read it out? So if you do find a signal, does it immediately have a way to distinguish between an actual signal and a systematic failure? Yes.
Yeah, so I think that's part of the reason why we're also trying to compare not only against periodicity, but also against like randomness. Because I guess you would sort of expect that systematic failures would maybe fall into one of those regimes that would either be quite random, like stochastic, or relatively periodic. So hopefully that if it is a systematic failure, you would kind of find it falling into one of those regimes, and you would kind of quantify it as being non-artificial in that way. Yeah, that's a good question. I guess we don't explicitly account for systematic failure. That would be part of like I guess cleaning the transit light curve data before you input it into the metric.